So if the fluid is unsteady and the velocity vector changes direction, then the same thing will do the streamlines. Okay, so the streamlines will change in time. So we define the streamlines very easily in a two-dimensional example. So streamlines are given by, you can get, so if you know the velocity vector, in this case, u and v, well, in this case it's two-dimensional, okay? If you know the velocity vector, u, v, w, then you can compute the streamlines, which in a two-dimensional case is just the slope of the velocity vector u, w, okay? So du by dz in that case, okay? By the simple equation written there. So definitions of streamlines. Close to a solid boundary, streamlines are parallel to the boundary because the fluid cannot hit the boundary. The direction of the streamline is the direction of the fluid velocity by definition because they're tangent. Fluid cannot cross a streamline, again by the same definition. Streamlines cannot cross each other, of course, same definition. Any particle starting on one streamline will stay on the same streamline. In a steady flow, streamlines can change with position. Can change position with time. Streamlines can be a family of curves that are instantaneously tangent to the velocity vector, so they can change in time if the fluid is unsteady. Path line is just the trajectory of individual fluids. If the fluid is steady, path lines are the same thing as streamlines. If the fluid is unsteady, then streamlines change at every delta t, for example. So the final path line or the trajectory will not be the same as the streamline because the streamline has been changing all the time. If you put together a bunch of streamlines, you can form a stream tube. Okay, stream tube by definition passes through a closed curve C. Okay, so all those blue streamlines that are passing through that closed curve, red curve C, they form a stream tube. And by the same definition, fluid cannot cross a streamline, therefore they cannot cross the surface of the stream tube. And the stream tube can change position if the streamlines do. Okay, so then we started looking at the kinematics. So we define normal or linear strain rates and shear strain rates. Okay, we did this simple two-dimensional example, and we find out the linear strain rates in this case. And I'm going to write down a couple of things. So for the linear strain rate, we find out the volumetric strain rate. Equals 1 over V, Lagrangian derivative. Oh, we looked at that. No, we looked at that before. That was, okay, this was the volumetric strain rate. Which in a one-dimensional case is that equation number 10. Then we looked at the shear strain rate. But before we also defined, I'm going to write this down because we're going to use them in a second. The velocity gradient tensor. Remember, the diagonal terms are the linear strain rates. Yes, so we looked at the shear strain rates, and we eventually define a strain rate tensor, which was Eij. Okay. And so the diagonal terms of the strain rate tensor are the linear strain rates, and the off-diagonal terms were half of the shear strain rates. Okay? No questions here, yes. So if the element is deformed by a shear stress, it could, doesn't have to, but it could acquire rotation. Okay, so remember that little square that we used. In this case, has been shrinked. Okay, and it could actually acquire rotation. And so we looked at the vorticity of the fluid element. And the vorticity, we looked at the angular velocity, which is the average of the change of the two angles, alpha and beta. And by definition, vorticity is twice that change in angle, so twice the rotation. Okay. So if you look at twice the rotation in the example, and you look at the third component, so the rotation along the x3 axis, you get to the familiar, I suppose, familiar definition of vorticity. Okay, so this is the vorticity that you can also write down in Tensor notation as the alternating tensor UK xj. Okay, this was the vorticity term. Related to vorticity, we saw circulation. Right? We remember Stokes' theorem that relates a line integral to a surface integral. And the line integral along a closed curve C is equal to the vorticity integrated over the area bounding that curve. And we know that that is equal to the vorticity, so we can write down the line integral of that velocity vector as the surface integral of the vorticity. Okay? And we call that a flux of vorticity. So a flux of vorticity through an area is equal to the line integral along the closed curve C. Okay? So the line integral along a closed curve C is called the circulation of that vector. Okay. So we define the streamlines. I don't have to. 5 minutes. These have to stay here. So we define the streamlines. Now we can actually define the stream functions. Okay, and to define a stream function, we're going to define a function that satisfies the conservation of mass. We will look at conservation properties next time, but we're going to use conservation of mass today just a little bit. Okay. So we want to define a function that satisfies conservation of mass. We remember the volumetric strain rate, this one, okay? And the volume of this fluid particle is inversely proportional to its density. Okay, which makes sense. So we can write down the volumetric strain rate as 1 over rho d by dt of density, which you can expand the terms and see that this is how it looks like. Okay, so we just change the volume by density. That's a minus, yes. If you expand all the terms, you will see that this is how. We don't have time. Okay. Trust me. Or you can go to any textbook and see. Okay. And so this is what, when we do the conservation of mass, this is what actually we're going to call the continuity equation. Okay? Which basically says conservation of mass in a fluid element. Okay. And then we're going to use something else that we are going to define later, which is the Boussinesq approximation. And the Boussinesq approximation says that along a streamline, density doesn't vary much. Meaning that if you define density as a mean plus a fluctuation, within the Boussinesq approximation, rho prime is much smaller than the mean. Okay, so the fluctuations of the density are very small. So the density doesn't vary much along the fluid path. So if density doesn't vary very much, its derivatives are going to be very, very small. Okay, so we can say that the continuity equation reduces to 0 equal d by dx of ui. Okay, because this term are very, very small.
Rho prime and rho bar. What are these?
So this is a mean plus some fluctuations. Okay? So within the Boussinesq approximation, rho prime is very small. Okay? So along a streamline or along the fluid path, density doesn't vary much. Okay? So its derivatives are going to be very small, and so we can neglect these derivatives over here. Okay? So we can say this is equal to 0, and so the continuity equation reduces to that. For a two-dimensional flow, this is du by dx plus dv by dy equal to 0. Okay? For a two-dimensional flow. And in this case, for this two-dimensional flow, which satisfies the continuity equation, this means that the flow is divergent free. Okay? So the divergence of this velocity vector is equal to 0. Okay? So the flow is divergent free. If the flow is divergent free, then we can define a function psi of x, y, it's two-dimensional, and time. And we're going to define this function such that u is and v is minus. Okay, so if you define this psi function that way, that satisfies the continuity equation. Okay, we can just replace that into the continuity equation, and that satisfies the continuity equation. So we basically just define a vector potential which we call psi, which is going to be the stream function, such that our velocity vector, two-dimensional velocity vector, is equal to this. Okay? So that is going to be our vector potential. So we just define a stream function psi for this no-divergent flow, two-dimensional. And we're going to use that stream function to plot our velocity vector, for example, or to visualize our velocity vector. How are we going to do that?
Is psi the vector potential? Is psi the...
Psi is the vector potential, yes,
Okay.
of that divergent free velocity vector. Okay, so why this stream function is useful, you will see in a minute. So if you remember the equation for the streamline, the two-dimensional streamlines, or the streamline for a two-dimensional flow, there was dx du, dy dv, right? That was the equation for the streamline of a two-dimensional vector. And so now we can write the streamlines in terms of the stream function. Okay? If you do that, dx is u, d psi dy equal dy v, which is minus d psi dx. Okay, so d psi dx d by dx of psi dx is equal to psi d by dy dy equal to 0. Equal to, sorry, yes, equal to 0.
Yes.
Yeah?
Yes.
Okay, yes. So this is the equation of a streamline. So this means that dip psi is equal to 0 along a streamline. Okay. So this means that the stream function doesn't vary along a streamline. Or that a streamline is a line where the stream function is a constant. Okay? So the streamline is our stream function. So we can make a simple example. X and y. Okay, this is x, this is x plus.
Can you repeat the statement again? The meaning of decide what is that?
So along a stream, so this is the equation for a streamline, okay? Which is this. So this means that dip psi is equal to 0. So along a streamline, the stream function doesn't vary. So a streamline streamline is equal to psi equal a constant. Okay, so the stream function is constant along the stream. So x dx, then we this is v dx, and this is minus u dy. Okay. So for example, we can look at the and these are two stream functions. These are two streamlines or two stream function. Psi of this case, or that case. Okay, these are two different stream functions or streamlines. And we're going to compute the volume rate of flow across dx. Which is dx dy. Okay, so across this line segment here, dx. So we have two streamlines or two stream functions, and we want to compute the volume rate of flow across this dx line element. Okay. What is the volume rate is going to be v dx. Okay, so v dx minus u dy, and we can substitute the stream functions here, and v is minus psi x minus u dip psi dy. Okay. There's a dx missing, and there's a dy is here. Okay, and that is equal to minus dip psi. Okay, which is the same thing here. There. So the volume flow rate across this line segment over there between these two streamlines is equal to the change in the stream function. Okay. So the streamlines, which can be instantaneous if they change in time or they can be fixed, are lines of psi equal constant. Okay. And the flow rate across these two streamlines is equal to the change in the stream function. Okay? So if you know the value of the stream function, here and you know the value of stream function there, then the rate of flow could be mass transport, could be volume transport, is given by the difference between the two stream functions. That's why it's useful to plot, if you can define a stream function in a divergent free flow. Otherwise you cannot define a function that satisfies the continuity equation. So for a two-dimensional flow that is divergent free, you can define a stream function. For a three-dimensional flow, you couldn't do it. So you have to define a two-dimensional flow. It could be in the xy plane or it could be in the yz plane. We're going to see all the examples now. If you define a two-dimensional flow, which is divergent free, then you can define a stream function that satisfies the continuity equation. Okay? With the stream function, if you know u, you know the stream function. If you know v, you know the stream function. Okay? So you know the, for example, the velocity vector in u and v. So you can plot the stream functions, and you know the value of the stream function. Okay? So the mass transport, the volume transport, once you plot all the stream functions, is equal to the change between the difference between the two stream functions. Okay? That's why stream functions are useful. And they're useful because you can look at the atmosphere and the ocean, for example, and define a stream function psi. Okay? Here we are looking at the atmospheric circulation. This is latitude. Okay? So it will be my y, and the y-axis is height, z. Okay? So in this case, we have defined a two-dimensional flow in y and in z. Here the flow is divergent free, so we can define a stream function. So instead of plotting velocities, we are plotting stream functions. Okay? From the velocity field, I can define a stream function. Okay? So every line that you see there, so different colors, blue and red, but basically every line, in this case are closed lines, are closed stream function. Every line has a value. Okay? And so the difference between a pair of stream function is equal to the mass transport in the atmospheric flow. Okay? In this case, you see some closed circulations. This is the equator. Okay, this is the equator. And you see this upward moving. Okay, the velocity field here is positive. And then the circulation is closed by this downward. And actually, you will see in atmospheric dynamics that this is called the Hadley cell. There's another Hadley cell on the other side of the equator. And then there are two Ferrel cells in the subtropical regions. So what we're plotting here is, this is latitude, so it will be my y, and this is height, my z. This is the equator. I'm plotting a stream function psi1, and then I'm plotting a stream function psi2, and so on and so forth. Okay? Given the velocity vector that I have of this two-dimensional flow, I can plot the stream. I can compute and then plot the stream functions, and I know exactly how much mass transport I have here and here, because the mass transport or the volume transport is given by the difference between the two stream functions.
At the initial point, how we know the velocity seems to define the stream function? Is it that is that from we get from the instrumental data or something?
Yes, in this case it's a model.
Okay.
In this case it's a model, so I have W and I have V. Okay, so I have my two-dimensional flow. U is V and W. So I have my velocity vector. I compute the stream function. I plot the stream function, and then I know exactly what's the mass transfer between each two stream functions. Okay. And I can do the same thing in the ocean. Okay. This is again latitude, and in this case is depth. Okay. I have my velocity vector v and w, meridional velocity and vertical velocity. It's a divergent free vector flow. It's a divergent free flow. So I can define a stream function, and every black line that you see there, it's a stream function. Okay? And so I know that this stream function has a value of 24 Sverdrup. Sverdrup is a unit of measure that we use in the ocean. 1 Sverdrup is 1 meter cube per second 10 to the 6. Okay, that's 1 Sverdrup. We will see it in ocean dynamics. So this stream function has a value of 24 Sverdrup. This stream function has a value of, I don't know, 22 or 20, I don't remember. Okay. So the difference between those two stream functions is 2 Sverdrup. So the transport that I have here is equal to 2 Sverdrup. Okay. Because it's just the difference between the two stream functions. Okay? Any question? You don't seem convinced. You're not convinced? You are?
No.
You're not convinced?
Convinced.
Huh? You're convinced? Who's not convinced?
I think I missed the computation. If we have 2 and 4, then what's the difference? The mass transport. You said 2.
So if I don't remember that case, but psi 1 is, I think, is 20. Well, we'll see in a second. So if this is 24 and this is 24, this is 18, so this has to be 21. Okay, 18, 21 plus 3, 24 plus 3. Okay, so the contour interval is 3. So if this is 24, this is 21. Let's see, 24, 21, 18, 15, 12, 9, correct. Okay, so psi 1 is 24 and psi 2 is 21. So how much transfer of mass or volume I have between two streamlines is just d psi, which is 3.
And the direction?
And the direction in this case, if it's positive is clockwise by definition, and if it's negative is anti-clockwise by definition. Same thing here. If it's positive values is clockwise, and if it's negative values, that means that it's anti-clockwise. Okay. So in this case, we have 24 on the outside. Now this is going 20. Yeah, correct. Okay, that's how you define your stream function. So if it has positive values, it's clockwise, and if it has negative values, it's anti-clockwise. So this, you know that the flow here is going here. You have something like this. Okay, here you have your 24. Yeah, many more stream functions, of course. Okay, then you have this 2. Okay, this is positive, this is positive, this is negative. So this means that the flow is going like this, like this, like this, like this, like this, and here the flow is going positive, and here is going negative. Right, by definition of the stream function. So the flow is actually going like this, and here you have 2 smaller cells. Okay. And we'll see what they are in ocean dynamics. Okay. So by plotting the stream function, you know the direction of the flow and the intensity of the flow.
Yes.
Okay, so now we're going to put together deformation and rotation. And we're going to do it through relative motion near a point. Okay, so the fluid element can deform and rotate. We'll see that through linear strain rates and shear strain rates. So there can be deformations and rotation. Okay. So we want to put these two together. So the relative motion between 2 points is the sum of the motion due to local rotation, okay, due to shear stresses, for example, and local deformation. I'll call this x2, x1, and x3. So at point A, we have a velocity vector u, point x, and then we have at point B, we have a u plus du, and this is dx. Okay, so we're going to define the relative motion near point A, and we're going to put together deformation and rotation in order to describe the kinematics of the flow. So here we have u in xt, and here we have u plus du in x plus dx of t. Okay, at point B. This is in A, and this is in B. Okay, so we're going to do Taylor series again. So velocity ui at xi plus dxi, so at point B, is going to be the velocity at point A plus the Taylor expansion di x1 dx1 uj x2 plus I. Which is equal to okay, just doing a Taylor expansion on xy. And this can be written as
U or X? The subject,
the what?
the X3, do I?
Ah, thank you. dy. Okay. So we're going to call the relative motion at time t ui xj xj. Okay. This is at 9, yes. But we know what this is the velocity gradient tensor. And the velocity gradient tensor denotes both, if you remember, deformations and rotations. Okay. So we know already that the velocity gradient tensor is going to give me both the deformations and the rotations. So now we can decompose the velocity gradient tensor in order to separate the deformation and the rotations. We're going to separate the velocity gradient tensor into a symmetric and an antisymmetric part. Yes? Okay. So here I'm doing nothing. I'm half of the velocity gradient tensor plus half of the velocity gradient tensor, and half of this minus half of that. Sorry. Is equal to 0. Okay. But this is going to be symmetric, and this is going to be antisymmetric. And what is this term? The strain rate tensor. Okay. That's the strain rate tensor. And this is actually, so now half of the rotation tensor. Okay, so we separated the velocity gradient tensor into a symmetric and antisymmetric part, and the symmetric part turns out to be the strain rate tensor, and the antisymmetric part turns out to be half the rotation tensor. And what is written there? No point. So the antisymmetric tensor Rij, its diagonal terms are equal to 0, and the off diagonal terms are equal and opposite. And the strain rate tensor Eij, we know that the diagonal terms, do you remember what they were? The linear strain rates. Okay, so they were the I. Okay, those were the diagonal terms, and the off diagonal terms this were half the strain rates. Okay, and the rotational tensor, the diagonal terms are equal to 0. Okay, because this is 1, 1 minus 1, 1, and so on and so forth. And the off diagonal terms are equal and opposite. And if you put the, if you substitute, we're not going to do it, you're going to get minus omega 3, omega 2, omega 3, this is the opposite of this, minus omega 2 is the opposite of this one, and this is minus omega 1 and omega 1. Okay, if you substitute the indices. Okay, no need to do it. Do you want me to do it? No. Yes?
No.
No, right? There's no point in that. Okay, one more.
Because
Well,
I need to do it.
okay, we're just going to do one. Minus omega 3. 1 dx2 minus 2 dx1. This is minus omega 3, right? So that will be this term. 1 to 2, 1. Yeah, so on and so forth. Omega 1, this one. 3 x2 minus u2 x3, and so on and so forth. Yep. Now you should remember that we define vorticity. Question?
The alpha has been factorized out.
Huh? Come on.
The alpha is factorized out. This is just the inner component. Okay. I'm good.
Good. So we define the vorticity as the curl of the velocity vector, and we also saw that it can be written as the alternating tensor UK xj. Okay. And if you start substituting all that into the rotation tensor, you can show, and you can do it if you like, that the rotational tensor can be written as minus the alternating tensor vorticity. Okay, you just substitute things in there. For example, R21 is going to be minus 2, 1, 1 minus epsilon 2, 1, 2 omega 2 minus epsilon 2, 1, 3 omega 3. What is this? How?
0.
This is 0. What is this? 0. So R21 is equal to, how much is this?
Negative.
Negative 1.
Minus 1. Yeah.
Okay. So the vorticity in the third component, so along the x3 axis, is R21. Okay. Which is this?
Yes.
So we'll finish in a second. So the relative motion near a point. Do I need? Yes. So you remember the relative velocity at time t was this. Okay, that was the relative velocity at time t. We know that this is equal to the symmetric part and the anti-symmetric part. And the rotational tensor is equal to that. So the relative velocity at time t, dy, is the strain rate tensor plus half of the rotational tensor, dxj. Right? This is equal to this. So this is the strain rate tensor, dxj. And then we can write the rotational tensor as this. So minus dijk omega k of dxj. Okay, so we have the two components separated. You can also show, if you like, that this is equal to ijk dx j. Okay, so you can demonstrate this, and you can. Well, that's okay. You can show that velocity, the vorticity vector, can be written that way. So you just write the relative velocity time t equal to the strain rate tensor,
The F,
the
the 1 over 2, why is it relative?
good question. Minus half. Thank you.
Yes.
So the strain rate tensor, so the relative motion is given by the strain rate tensor, and then minus is equal to this, so plus half of the vorticity. This is it. Okay, by using this. So now we have two separate components that describe the relative velocity at time t. One is given by the strain rate tensor, so deformations of the element. And another one, which is given by the rotational tensor or the vorticity, and this is giving you rotation of the element. And the rotation of the element is at half the vorticity, so the rotation. The angular velocity is half of the vorticity, which was twice the rotation. Okay. Minutes, not bad. Okay, stop me anytime. Now we're going to summarize. We have the velocity gradient tensor, so we're here, okay, and we separate it into symmetric and antisymmetric part. Okay. The symmetric part is the strain rate tensor, EIJ, and the antisymmetric part is the rotation tensor. The rotation tensor has diagonal terms equal to 0, and the off-diagonal terms are equal and opposite. So the relative velocity is going to be given by deformations and rotation. The deformation is given by the strain rate tensor, and the rotation is given by half the vorticity, so the rotation. Okay. And I'm done 2 minutes before. I was quick, but I did it.